Hello. I hope that you are enjoying the whole lecture series. And today we'll start with and we'll see the traveling salesman problem. So we'll define that the traveling salesman problem and know about that. So the traveling salesman problem is basically said that given a list of cities, the distance between each of the city, what is the shortest possible route that visits each city exactly once and return to the origin city. It means that there is a large graph and you have a graph and you have a vertices and nodes. The vertices means nodes and you have edges that could be link or connections or distance routes. So you have a given n number of cities and you need to find out the shortest possible path for that traveling salesman that he want to visit each city exactly once and he want to return back to the same city from where that traveling salesperson had started. Then routing problem is basically like for example, in case of Germany, there are 15 largest cities, and they created a graph like this that actually route like this that could actually covers at most 2000 kilometer, and that will cover 15 different cities of Germany. And the application of traveling salesman problem is in DNA sequencing to determine the order of ATGC, adenine, thymine, guanine, cytosine. Then a slightly modified traveling salesman problem could be used on such many applications like DNA sequencing. Then it appears as a sub-problem of DNA sequencing. And thus, DNA sequencing is becoming even much harder problem to be solved. Then we'll see that TSP, traveling salesman, can be modeled as undirected weighted graph, such as cities could be represented as vertices, paths could be represented as graph of edges, graph's edges. So path could be edges of the graph. Then path distance could be weight of those edges. Then there are two possible ways that symmetric TSP, that where the distance between two cities are same and in the traveling uh, in the opposite direction when you travel, then you have the same amount of distance that you need to cover, means it's equal weightage amount of weightage that were required in both the direction, towards forward or towards backward. So forward or backward would have same amount of distance and the amount of uh, investment that is required to be traveled. So basically, this forms undirected graph. And the example of this is road. So roads are basically have the almost same amount of distance for going forward and backward. Then asymmetric TSP, basically the both the direction means going forward and going coming backward might not have the same amount of distance or may have the different amount of effort required to be traveling. For example, in case of rivers, then this is the example that you can see that this dark edges are giving the traveling salesman. So 3 plus 1 plus 1 plus 2. So it's 7 is the traveling salesman route possible. For this, you have to solve it as a your own part. So you solve it by yourself. We solve this one. You solve this one. Then the traveling salesman basically actually the polynomial time factor harder as compared to the Hamiltonian cycle. So, what does uh, uh, in the theory of computation or theory of algorithm and analysis says that the Hamiltonian cycle problems is not more harder than the polynomial factor, harder than the traveling salesman. So, the traveling salesman problem is much harder as compared to the Hamiltonian cycle. And they said that if you can solve Hamiltonian cycle, then you can also solve traveling salesman problem because it is not polynomial factor harder than the means the difference is just related to polynomial factor, and Hamiltonian cycle is all means polynomial factor easier to be solved as compared to the traveling salesman. You can also infer from this statement. So this statement could be written like this. So this symbol, this less than equals to P says that not more than polynomial factor harder than. And TSP thus is a NP complete problem. This whole thing that circuit set 3CNF, cliques, subset sum, vertices cover, Hamiltonian cycle, and TSP. These are said to be NP complete because these are reducible to each other, and they are actually not more than polynomial factor harder to each other. So these are basically the NP complete that was being defined in the set. So TSP is said to be most hardest as compared to these problems. Then you have the NP hard problem. So NP hard problems is like brute force could solve it. So for example, in the traveling salesman problem, you can solve it in the brute force way. Means you can try all the permutation, means ordered combination to find the shortest route. And the running time complexity for doing this brute force search is order of n factorial, which is taking the factorial time, where n is representing number of cities. Then the solution becomes impractical when you just want to do it for the 20 cities. Means 20 factorial is a very large number. That's why this whole thing becomes very complicated to be solved because order of 20 factorial is very large. Then next, we'll see the approximation, TSP approximation algorithm. Because TSP is NP hard, so it's very hard to be solved just for the 15 vertices. So even the for the few vertices, like 15 vertices, depending on the computation power, the TSP algorithm might fail. If you have lower computation, then it will even fail for the V equals to 15 if you want an exact solution. Then even the polynomial algorithm also fails on big graphs. So I'm talking about very, very large graphs where vertices are about in the millions or billions. And these type of graphs are said to be big graphs. And these are like having the V and E equals to millions or billions of edges and vertices. For example, even the minimum spanning tree, like Kruskal's algorithm and prims, which could be solvable in polynomial time, or shortest path algorithm, disasters or Bellman Ford, which could be solvable in polynomial time. But they also even fails out because of the limitation of computing power. Even that single machine with 64 GB RAM or 512 GB RAM, even 1000 plus GB of RAMs, sometimes fail to solve such large and big graphs. This is what I'm talking about. So single machine can't solve a very, very big graph. So solution could be possible is parallel computing environment might solve these type of large big graphs. For example, Apache Spark X means Apache Spark GraphX is one of the parallel computing environment where you can compute those NP like problems or even polynomial time problems for a big graphs. So for big graphs, you have solution of Apache Spark GraphX. Then the TSP approximation algorithm that actually provides the approximate solution for to a given graph. So next we'll see what are the TSP. We'll see exactly two TSP approximation algorithms that can provide some approximate solution for a given graph. So next we'll see traveling salesman problem TSP approximation algorithm. I hope that you like this traveling salesman problem and you attempt to solve it